Hello, everyone. Welcome to another Wolfram Language Design Review for version 14.3. We are talking about control and system modeling. This is part two of a discussion about this. Last time, we talked a bunch about the concept of system model validation, um, and we got kind of hung up on these ideas about temporal always and various kinds of temporal conditions. How have we made progress? Have we made progress on those things?
Since yesterday. I can share something that it outlines the analog, if you like.
Can you send it to me, please?
Um, Hold on 1 second. Uh, I didn't have time to finish this,
Okay.
so it's a bit rough. Okay.
Okay. So just sort of to bucket what's going on here, we have sort of the cleanup of we have our attempt to guess how this is going to work for time series and so on, which we can then feed back into the design for this.
Okay, it should be sent, but I use it to send to with our cloud, so it usually takes a little while. Like send a notebook.
Yeah. Okay. I know
You
you've
get it?
been working on many different things, so the fact you've managed to produce anything since yesterday is impressive. Um, okay.
Yeah. So what I,
Do we
the
have Jose here?
no,
We need to.
I'll send him an email. Yeah.
he should be around. We usually have a meeting at this time, so.
Okay. So one issue is this, this thing here, always and eventually,
Mhm.
they feel morally similar to for all and there exists.
They are.
And somehow, and these, so just so I understand this, I mean, yeah, I mean, so I mean, it's almost that should be always and eventually. Um, hmm. I mean, the concept of always and eventually is very temporal in there, and so kind of feels like they need another modifier, different modifier. But then these other things like temporal until,
Mhm. These
what does
are,
that do again?
if you go to that ref page, it's easiest to explain from that. It's basically, the simplest case is, you know, the the B1 or expr one is false, is true, and expr two is false. And then when expr two goes true, the whole thing goes false. See that's the very first case you're pointing to there.
Okay. So wait a minute. Until, so I mean, if we had it, this is defining temporal until defines a span of time. Is that true? In the end.
It it's a filter from these two booleans. See what I'm saying? It comes out as a new Boolean function, a temporal Boolean function.
Which is one of these kinds of functions. T1 is less than T2 is less whatever, or what?
Um, uh, uh, I, I mean, it could always be expressed like that. Any Boolean function could be expressed like that, one way or another.
So in principle, there's a temporal expand that one can imagine, just like piecewise expand or something like that. that would take some combination of sustains and untils and all that.
Okay, but these are also all built to be nested, right? So, kind of, they're.
I get it, but I mean, I'm saying,
Yeah.
as I understand it, there is in principle an expansion that you can do that will resolve it all into a, some kind of CNF-like form in terms of native inequalities and so on. I would assume.
I don't know. I think we tried to do that, but didn't. But maybe you're right.
I think it has to be true at some level. So
No, but
therefore,
the problem is that there's a bunch of state-dependent stuff. If it wasn't state-dependent, like what happened earlier matters to what happens later. If it wasn't state-dependent, I think you would be right. Now that
I think it's right. Even I think. Well, go ahead. Go ahead.
Like that temporal until, I think, is state-dependent.
Let me understand what temporal until does again. It's true in the intervals where Tx per 1 is true. Okay. So it's finding. So let me just understand. What quantity until that first becomes true? I mean, I could imagine a similar thing for a polynomial, for example. You're scanning from the left as x increases. Why? Let me understand. Symbolically, why is it the case that temporal until of a comma b is not simply equal to a, and then the chips fall where they fall? There's an a of t as the first argument, right?
Mm-hmm.
And so why isn't the correct description here temporal until is a of t until b of t first becomes true, at which point the result is false? Right, so if a of t was indeterminate or something, then it could pick that up, except that it has the constraint that as soon as b of t becomes true, then the game's over. And the whole thing is false. Is that not correct?
I'm not sure. I mean, maybe we should try. And also, I think there's that last piece of semantic I'm wondering about, but I wonder if we really need that, So for the whole thing, do you see that very last use case there? Like
what in this one here?
Yeah.
By the way, Jose has joined.
Okay, great. I'm confused by that last use case.
So am I a little bit. So, Sergio, why is that the case, actually?
So it turns out that there are like there are there is a strong until and weak until in temporal logic. And this is kind of here we're actually making a choice, basically.
Well, should we be making a choice? I mean, it's like less than or less than equal to. Is that correct? Is that what you mean by strong and weak?
No, probably not.
No, basically no. It's just this choice of like if the second expression never becomes true, it just stays false.
What just stays false?
The final result. So as you see, there's another at the right, really.
I don't think that's correct. I don't think you want that. The fact that it never happens, everything's hunky-dory until the thing blows up. It never blew up, so everything stayed hunky-dory. Not because it never blew up, it's dead in the water from the beginning. See what I'm saying?
I think because we are thinking in terms of T_1, if you look at that description in that second cell, it's temporal until is thought of as not T_2, and then some conditions.
Okay.
So it has to start with not T_2, and then and then from there T_1 has to be true until T_2 is also true.
All right. I'm somewhat muddled here, but I want to zoom out a bit. Okay.
Mhm.
And I want to understand these, let's say, temporal delay, for example.
Yeah. Go when you want to talk about it, go to its page.
Okay.
We spent some time getting that, you know.
I think you should mark off the delta in that picture. You should mark that this is T1 and then T1 plus delta.
I
You should
see.
mark T1 and then mark T1 plus delta.
Okay. Yeah.
So the simple case, it's a pure delay.
Right. In the other case, it might expand or contract the region of truth, so to
Right.
speak.
Yeah.
Okay. So in some sense, this is a transformation on the variable t in B of t. Right?
Yeah. Yep.
Temporal sustain.
We had more, and we've gone back and refined these. And so we've done a round of sort of doing actual verification work and trying, using them. And we've done several rounds.
True over time intervals, but T expert is true for at least min. I see. So it gives up after a certain amount of time. Even if it's true, the valve is open. After a certain amount of time, there's no pressure anymore because all the gas leaked out or whatever.
Whatever.
That's the idea.
But also, if you think the kind of thing you express here, like, for instance, in many systems, it's okay that you run over some limit for a limited amount of time. Like the battery can be too hot for a little bit, or, without blowing up the car.
Mm-hmm.
So you can often surge, and overload something for a limited amount of time. And many specifications are written like that too. It's like, if you go over something, no more than this type thing.
Yeah.
So it's expressed as a common type of requirement.
Okay. So this is all, the outer thing. So let's look at what one of these looks like. Okay. There's always, okay, if I just say system model validate, is there an implicit always outside of all these secondary
No.
templates?
No, you write it. Temporal
Okay.
always T, because we need to scope the variable, the time
I
variable.
see. Okay. All right. Okay.
Because we want to have access to it and be able to use it, and we can't just introduce it out of kind of nowhere.
But hold on a second. I don't understand that scoping, because you've got system model validate
Mhm.
has a scoped variable, but where's the model?
It's the system, Aerosim in that case.
Okay, but how do you know Aerosim has a time in it?
Yeah.
But this time is scoped.
Yeah,
How
but
do we know how to connect that?
No, but it has a time in it, but we never explicitly use that as a variable. Everything you simulate in System Modeler is over time. It's always dynamic. It's always over time.
Okay, but what's the variable name for the time?
It doesn't have a name. We introduce it when we need it, for the rest of the system.
So here, for example, that says T, but that
Yeah.
T is just a decorative T.
Yes.
I see.
And the thing is that what comes out when you simulate it is kind of in that notebook I sent today. Look at that, a very simple system, but it has like 47 signals in it.
This which notebook? The one you just sent?
Yeah. Scroll down just a tad. Look, stop. See that?
Yes.
The second group, the sim variable names. Those are all, that's a very simple system.
Yep.
But those are all the, variables, the functions of time.
Yep.
And when we return it, we return an interpolating functions. But in many ways, you could, interpolating function and time series is in many ways the same thing.
Okay, but basically all of them have no explicit variable mentioned. They are merely functions, or time series is sort of like an interpolating function.
Yeah.
That that eat. Okay, so the second thing.
So we package it up when you ask for it like that, so that it can fit with the rest of the system.
Okay, but so system model validate.
Mhm.
Can I just feed it an interpolating function as its first argument? Don't see why I shouldn't be able to.
No.
Why not? It's got a time variable on it.
But what's its name? How do you refer to it?
How do you refer to the value of the interpolating function?
They have all the names. So they
No,
all
no,
have names.
I understand that. I understand. But for other uses of this, the validation, right? So the issue.
I mean,
is
if you want to bridge into the rest of the system, you get yourself one of these interpolating functions, and then you go and do everything you can do with a function in the system, basically.
I understand, but for this, what I want to do is I want to take that interpolating function. I want to take this thing here, right? That result as an interpolating function, and I want to check, does it satisfy, eventually, temporal eventually, 6,000 or something? See what I'm saying?
Mm-hmm.
So how would I do that? So in other words, rather than digging into all of the variable names and all this kind of thing, there's got to be a way to take the, one thing is you've got the simulation. It's the first argument of system model validate.
Mm-hmm.
And
Which is even though it's a system itself defines many things, right? So you saw those 41 functions there that came out of the other notebook.
Yes.
Okay. So you want to validate relationships between all those that they satisfy, and perhaps something external that your requirements puts in.
Sure. Right, but I might just want to say, if I just have a plain interpolating function, I might want to.
But then we need to fine, but that's not a system. An interpolating function is not a system.
I understand. I'm looking for a uniform design because we're going to have this temporal logic stuff. It's a lovely thing,
right?
But let's do it in general. So let's think about what we would need to have a validator for an interpolating function. Okay.
Mm-hmm.
So, in this case, okay, I mean, system model validate might do one thing, but you might have a temporal validate or some such other thing.
Absolutely.
I don't even know why it's temporal. I mean, these things are, the only thing is
temporal.
What's that?
They're temporal.
Well, they're a single variable, and we're thinking of that variable usually as time. I don't know whether it's always time. I mean, we could imagine it being a parameterized distance, an arc length, for example, that always increases somehow. Okay, but so let's just think what it would look like to do this for an interpolating function. Okay, what would be the right design for these always and eventually and so on with an interpolating function?
Well, I mean, you have to give me applications. I mean, formally we can design it, but as I said, we have ruthlessly kicked out things that didn't come up.
Okay, but I mean, I think the application is I got an interpolating function out. I don't still have the whole system model. I just got one parameter out.
Right. And in the language, we use the names to refer to them. But
Well, I
let's
know,
say
but
that you had an association of interpolating functions or something, so we
Okay.
can maybe kind of refer to them. Or,
Well, let's take an example,
and it
Roger.
doesn't even have to be an interpolating function. It could be anything that just,
Let's
where
imagine you had a tabular where the successive rows are thought of as being successive times.
right? Yeah. Which is kind of close to a time series in a
It
way.
is close, right? So, but that's yet another. So the question is, can we validate the always, so to speak, across that,
Right.
where our thing is not a
I
symbolic
mean,
variable
we
to-
have for the purely discrete things, we have a bunch of stuff like all true, those kinds of things,
Yep.
which does, roughly that.
Well, I mean, okay, so all true is an interesting example here.
Which is also could have been said. That's also for all, basically.
Yes, that's right. I mean, but let's take a look at the design there. For goodness sake. What am I looking for? I am looking for meetings. Where is this? Okay. So let's take a look at that design. So all true list, comma, criterion. Okay, which is actually very similar in some ways to what we're doing here. And we've also got any true and so on.
Right.
So, I mean, a possible name would be always true and eventually true. And we could also imagine ever true. I don't know if that's right, but that's it's a possible naming structure.
Our initial name was sometimes true. It was terrible.
Yeah. So always true would be, the natural way to do that would be with a function f that's applied to t.
Yeah. And you
that
could
just
say,
says, yeah, go ahead.
f of t, less than or equal to something, like a constant, for instance. Is this always true, that f of t is less than that?
Yeah, exactly. So that would be.
But, so part of what we do here is that we use, numerical methods like simulation.
Hold on. There's a way to do this. There's a nicer way to do this. Okay, so this case, right? So one thing we could say is always true of f hash less than 4. Okay? Because that's our function now being put there. And
I guess in this case, you can assume that we only have one quantified variable.
yeah.
Yeah.
Absolutely.
Mm-hmm.
So, okay, so here,
What does all true do for arrays?
what kind of arrays?
Yeah, like a matrix.
I don't think it works on it. I think it just takes at the top level list.
Okay. So one.
I mean, let's just check that, but I think that's correct.
Yeah, I think it's correct.
Test parts of expert level.
Okay.
So it is capable of doing that. But I don't think that's that's not its most important feature. But now
the other thing, which wouldn't be hard to add into this, so temporal always also has a condition that can restrict the time for which it has to be true always.
Okay, fine.
You know, and it's implicitly set in system model validate because you pick simulation time, and that's the only thing it will check.
Yeah, okay, fine. But that's a system modeling.
Sure, yeah, yeah.
This particular thing here, you know, we could do symbolically for arbitrary expressions. I mean, if we wanted to, you know, the following thing would work, right? Always true sign of hash less than, you know, 2. Would just
Right, but
return true.
I mean, we already have this. It's you know, the verifier we have is resolve. You know, if we run for all in resolve.
Yep. No,
But
this is just a shorthand for that.
No, but it in practice it doesn't work for anything but polynomials.
Okay, that's a different issue. That's a different issue. Okay, but let's look at this. I mean, for an interpolating function, it's going to work, at least over a finite range.
Mhm.
I
No,
mean,
I mean,
you know,
with
always true could
numerical-
have
With
Yeah, go
numerical
ahead.
methods and some qualifications, because it's
like by default, it would only look over the range of the interpolating function.
yeah, but it can still make mistakes, okay? Because our interpolating function, if you just look at the data points,
I get it.
doesn't guarantee in between.
Yeah, I get it.
Okay.
Okay, so, but let's come back here to the case of interest here, where instead of a function f of t, you are using a system model symbol, you know, what I'm going to call system model symbol, although that's, you know, that's its overly dignified name. See what I'm saying? And we might just use strings otherwise. Right?
Yeah, right.
So now it's quite possibly the case that always true. Yeah, I mean, this is tricky. I mean, might not want to evaluate until you resolve, for example. Just as this might not want to evaluate until you say system model resolve or validate or whatever.
Mhm.
Okay. But, okay, with respect to sustain or until, so, I mean, those are all, given my function f of t, those are somehow,
They all take basically effectively what you would think of as pure functions. You know, or interpolating function head or time series head. You know, they don't have
do
any
they?
yeah.
I mean, here they're taking b of t.
Yeah, I shouldn't have written that. I mean it implicitly it depends on t, but I'm never sort of showing the t. I probably shouldn't have written that. I
Now
was
I'm
trying to
even
be
more
extra.
confused. Because this isn't right. This should say function, you know, t, that function, right?
Yeah. Although we could probably make that work if they're all within a scoping construct. We can make that. Yeah, that I take
It
it
could
back.
work within the
No.
scoping
It's
construct.
fine. It's fine. I was ignore me for a sec. I have to think.
Yeah,
No,
okay.
it's fine what you did. Okay, my bad.
Yeah,
bad.
because I think only
No,
the
my
one
bad.
argument form
Yeah. My bad.
is the pure function.
But I was thinking of the sustain until and all those guys. They
Well,
never.
How do they work?
Sergio, what happens if you give an expression of t inside one of those? That should work, right? When they're embedded.
Yeah, that's fine. I mean, if you like, you can use explicitly t there if you want.
You do that. Okay, fine. Because the t is scoped outside. Fine. You know what the t to look for.
Yeah.
Yes. Okay.
Okay, I'm thinking here. I mean, I just don't want to use temporal there because I think this is going to apply to things that aren't temporal. Sustained value, I don't know. I don't really like that very much.
We were looking for names for that. I can't even remember what it was called. What was it called, Sergio? It's a really bad name.
Temporal between was the first name.
Right.
Uh,
Sort
have a
of
list, yeah.
two special cases is that something lasts at least as long or at most as long. At least and at most. But this one has sort of both. At least and at most.
Yeah.
The names we liked, I think we listed in an excluded cell, right?
Oh,
below
yeah,
the
yeah.
list.
They're there. There are a bunch of other. If
But
you
in
go to
that
look at
notebook-
temporal sustain, I think, at the ref page, at the top of the note, there, other names. To
Wow.
last, to span, the blue
Wow,
cell
wow,
there.
wow. Oh, I see.
They're all pretty bad.
Those are bad. Yeah, but okay, but I'm still trying to understand the general semantics here.
Mhm.
Okay. So if we tried to have always true, but then the condition in always true is something which says, I'm very confused here because always true says for all t, this condition is true. I mean, it's equivalent to for all t, f
Yeah.
of t is less than 4.
Mhm. Yeah.
Okay, so now let me understand what, in terms of that kind of Booleanism, what is temporal until, for example?
Well, that second group, the temporal logic functions, they all return another logic function. See, if you have
Fine. But so does, I mean, I could say the same thing about
but
P and Q.
No, but the always and eventually they return a constant, true or false.
Fine. Look,
What's the difference?
and usually returns another Boolean function.
Yeah. But then they don't vary over time. They're all constant.
Yeah, okay. Constant over time.
Yeah.
Okay. Um, okay. Let me see. So, I mean, clearly all of this jazz is just going to work.
Yeah, not a problem. That's just fine.
And we can have sort of simplified versions of system model symbol that just work with all that stuff.
Right. And we do. I mean, that's
Yeah,
how
but
it
I
is.
don't understand how the system model symbol x dot y implicitly has the time variable in it.
I see what you're saying. Okay. So these names, they're defined relative to a system or a simulation, just as when you have names in a tabular,
I know.
those names
Yeah.
are defined relative to that.
Yeah,
thing.
except that these have one extra twiddle, which is they're actually, this thing
They're
is
actually
really,
functions of
this-
time.
this should really be called system model function.
Yeah.
Blah, 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 blah. Now, is it always that, or can it be sometimes system model symbol? I think it can sometimes be one and sometimes be the other.
Yeah. So the parameters are constant. That's the difference between parameters and states and so on.
Yeah, but-
Initial values are constant, parameters are constant over time. But the solutions, the state variables and so on, they vary over time.
Ooh. But I mean, then how do we know which things get an of t when we try to resolve an always true and which things don't?
because we have the system there, right?
No,
We
I
know.
understand. I understand,
Okay.
but it's a little bit hacky because when we're dealing with
I mean,
F,
it's like giving a context to saying these
more than
names
that.
are given meaning in this
I know,
Okay.
but I mean, in general, we're going to have to say, oh, with those names, they're either f of t or they're just f.
I think there are different properties for the system model. Some of them are system variables, some of them are you can query that model.
I get it. I get it. I understand how we disambiguate it, but in what it looks like, okay, when we say always true, right? We can say f of hash, but we can also say, you know, x dot y. I mean, you know, this, for example, would be a valid thing, except I don't know how to make that work. I don't know how to make that work because, I mean, putting in a time variable there is not particularly useful. What's it going to do for you? Doesn't help you. How do we make this know? I mean, if I say something like this or something where do you get what I'm saying? I mean, in other words, each one.
I don't know if Sergio has supported a pure string version, but strictly speaking, we always put in of time.
Except you don't when it's a parameter, unless you
Right.
have a
No, but we
constant function.
don't use parameters, right?
Yeah,
Why
you can
wouldn't
put
you?
parameters there as well, yeah.
Oh,
You just put them without the t, yeah, but yes.
okay.
Okay, so I'm sorry. This just sorry, I spaced for a second. Could you go back to what
Yeah,
you
so
said?
so the example I had 41 functions, as you call them, right? Functions of time. It also had parameters. I didn't list what those are. And you can use both those functions, and we always put of time, or you can use parameters, which are constant over time. So they don't vary over time.
So I could say of t here.
Yeah.
But
In the context of system model validate.
boy, this is a really weird syntax, I have to say. Let's understand what the fully qualified syntax would look like, okay? So I would say that the fully qualified syntax would be system model function system, comma, x dot y, blah, 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 of t. Do you agree?
Yeah, that's a super heavyweight thing.
That's fine. It's fine. I just want to understand what the fully
Yeah.
qualified version is.
Yep.
Then we can elide it.
Mhm.
Okay. So we've also got system model. Do we call it variable or symbol?
Symbol, I think.
Are you sure?
I mean, it's not a variable. We call them parameters. So, and that varies with every domain, how this is done, but mostly parameters are thought of as being constant, not varying. You could call it parameter or symbol is better because we're also going to have the things that are constant are initial values. They don't change.
Yeah. Okay.
And parameters like the resistance in a resistor.
All right. So it's okay. Just like we have symbols that have down values and other symbols that don't have down values and so on. It's okay to have some notion of a symbol name which is resolved somehow as to what kind of a thing it is. I don't have a big problem with that.
Mhm.
In terms of whether it implicitly gets wrapped with system model symbol or system model function. Do you get what I'm saying?
Mhm.
Um, okay. Okay. I think I have to go fairly soon here, so look, we're making progress on this. We have not resolved it yet.
So
Um,
if you want to take a break from this, we could scan through the control stuff and
yeah,
then
let's look at that.
schedule that next week, and then Sergio comes back the following week and we try to finalize this. That okay?
Yeah, I guess. I mean,
Okay.
where are we looking at here?
Not that one. That's just major application examples. Okay, why you want the validation.
Yeah, it looks cool. Okay.
Okay, so if you scroll down there you go, control design. So like just a small intro. So what we've been doing is to look at workflows, application examples, and whatnot, and identified a lot of crummy situations that led to a lot of code, and figured out, like, why is it looking like that? Why doesn't it directly accept, let's say that you want noise input. So why doesn't it directly accept like a random processor's input? Because that should be the right thing.
Yep.
And those didn't exist when we first designed a control framework, which is probably the reason. And so what we've done is to plug a lot of these things.
Good.
And one of the things we've also done is to significantly sort of improve the formatting, the typesetting of these control objects, the system state space model, transfer function model, and so on. They now have an attached cell that allows you to get a bunch of stuff.
So where is that?
Scroll back up. I think you scrolled too far down. Hold on. There we go. Attached cell. Attached cell is the attached cell. And
Okay, well, where is SSM1 defined?
It's defined way below. So it's if you evaluate
Where
it,
is
It's an initialization cell.
it's initialization cell at the bottom, not at the top.
Evaluate something there.
Okay.
And they're kind of nonsense models. They're just to have something. Okay. And so we say yes
I'm gonna
now.
have to go in a second, unfortunately, but okay, so let's say BFM is this, and what the hell happened? There's nothing attached.
I don't see the attached cell either.
Oh, okay. It should be. I asked Ying to test. I don't know why it's not appearing. Yeah, there's
there it is.
Okay, but I click to get the attached cell. Shouldn't need to click.
No, you shouldn't need to click.
So did graphic design work on this or not?
No.
Okay, so they need to.
Right.
So here's the thing that I would drive me absolutely bonkers with this, okay? I see that lovely plot. I want to get it. I need a button here, a click to copy button that gets me that plot, gets me the code for that plot.
That's a good point.
Yeah.
Yes.
See what I'm saying?
Yeah.
I mean, this is nice. It's very nice, actually.
Go back to well, we can stop there for a sec. This computes a bunch. What is it? Oh, a bunch of properties.
Yeah.
What? These are performance measures of the system.
Okay.
Okay. Like how the rise time, it's like a 0 to 60 time for a car type thing. Now, these are different ways of looking at it's better to look in a big, okay, let's look at the different ones. Okay. You can have
I mean, there's some click. The click is not going to quite the right place, but
so they're different. If you look at the next one too, the the state space. Oh no, look at the forms above. Scroll up. Yeah, those. Sorry. Yeah, here. The appearance, detail, structure, delighted. Yeah.
Yeah,
Okay,
click
in the
first one.
leftmost.
I
That one.
don't like these icons. These icons are not
No,
very
I'm
good.
fine. I'm fine. Do you see what they do?
Yeah, it's very
They
nice.
become relevant if the model is large.
It's very nice. I mean,
Right.
except that I really, really want to be able to get these as a, in SSM1,
Mhm.
there should be an option to display it in that form. Now this issue
There
has
is,
come up
there
in
is.
neural nets
There
as
is.
well.
There
Okay,
is.
how have we handled the thing with neural nets?
I don't know, actually. Can you set the display form there?
I think so.
I don't know, but we could go look at that.
Yeah, right.
We could check that.
Okay. Okay.
Yeah, but over here it's the appearance option. You can wrap it around state space
Oh, okay,
model again.
fine.
So
So the-
open those subcells there under appearance, maybe, because I think that those are better examples. No?
Yeah, they just show the yeah,
Where are
how-
the kind of cool ones? Yeah, this is a cooler one. Like if you
Custom
want to,
icon, right? You can provide an icon.
yeah,
Exactly.
and that's often if it's a complicated system,
Yeah, it's very
It's a-
useful.
and it leads to very nice workflows. They're kind of very understandable. But then sometimes we want to flip into sort of a super detailed mode, and I want to understand what the heck are all the details.
Yep, that looks nice. Okay, so big picture of this control system stuff. There's ergonomics are being
Yes.
improved, and
There's
whether-
one new function,
yeah.
which is pole zero plot. That's something that should have been there from the beginning. Not sure why it wasn't, but we've added it. It's one of those.
Okay,
that one.
okay.
Oh, and also if you look here above, I mean, I'm kind of giving you all kinds of little summaries here. We have provided in the Wolfram, in the WDR, a bunch of models now. If you click on that, you'll see a whole long list of models, and we have more to go.
WFR.
Next
No.
one.
Next one, WDR. Hope that works. Yeah. See, these are models. These are what we call plant models or system models that we
Right.
use for control design. But no, they're super easy to just get.
So now, what's the relationship between that and system model? I mean, look, what I would
This,
suggest doing-
these are actual, system model. System modeler doesn't mostly have components from which you can build models, but we also have examples of ready-made
Okay,
models.
let me remind you with NetModel, okay? That
Yeah.
NetModel picks from a repository with names from the repository. I think that's what this should do too.
It does, look.
Okay, so system model of inverted pendulum model just works.
Yeah, resource. Oh, what?
No,
No.
system
System modeler is
model.
for system. That's for system modeler. These are not. These are the.
We need to talk about this. This is
Okay.
exactly what I keep on saying about a repository for system models, okay?
Yeah, but
That's what we should
that-
have, just like NetModel. Yeah.
Yeah, that's a longer discussion because that won't really work with Modelica and that jazz particularly well. In system modeler, the product system modeler.
Yeah, I understand. But so let's talk about that. Okay. I understand what you're saying. We need some way of getting, models. I don't know what the convention is, how it works, how we pick up one rather than the other, et cetera, et cetera, et cetera. Get what I'm saying?
Mhm.
I mean, if the other ones are system model components, then maybe it's system component model or something.
We have to schedule a whole separate meeting for that.
Yeah,
That's
we need
that's
to-
like a totally different thing, and it probably won't be an easy or
Well,
even
I don't
doable.
think it's as hard as you think. If you can get this to work, I think you can get
This
that
is
to work
just
as
pure
well.
Mathematica. Dead simple.
Yeah, I know.
Very
I know,
simple.
I know. Okay, but we're trying to make it simple for users.
Absolutely.
The fact that implementationally,
No, but the
there's
other
something
one is
different
simple
underneath.
for users.
Well, I understand.
Simple in a
but-
different way than this is simple.
Okay, all right, fine. It's going to take us some time to talk this through.
Right.
This looks nice functionality. I should probably go.
So let's go on then with one round of controlled systems maybe next week, and we can wrap that, I assume. Or do you want to look at more of there, or do you not want to look at more there?
I think we're going to need, with control systems, we're going to need graphic design. We're going to need, I mean, there's going to be some iteration with that.
Yeah.
There's going to be, and this issue, we need to address this issue.
Well, that's a much bigger issue.
No, I don't think it's as big an issue as you think it is.
Super big.
Okay. I don't think it's as big as you think, but we're not going to have 6 different mechanisms. I mean, look, we could do this with the WDR for now, just as a convenient way to get examples. Maybe that's what we should be doing.
Yeah. I think we're providing a service for both our
Well,
users.
it's just simple examples. I mean, they're basically, it's not really an integrated thing. The right way to do this is with an actual repository that has all the right characteristics, but this is a good start.
Yeah.
I mean, what we should be thinking about is an actual repository that merges properly with the system modeler repository. I don't really see why it's different, but you can explain that another time.
Sure.
Okay. All right. Let's wrap it up.